Hello everyone. In today's lecture, I am going to talk about sign multiplication and Booth algorithm. This lecture is going to be useful to guide you through the final lab or the final project for the logic design. So in order to understand how Booth algorithm are going to work, we have to first derive the simple mathematical calculations that is necessary to understand the Booth algorithm. You can find a couple of videos on YouTube as well or on internet, but some of them I realize that they are not giving some accurate description of how we do Booth's algorithm. So I suggest you to follow this video and the examples that I'm going to solve to understand how Booth algorithm is working. So let's give a start. Sign multiplication. Now, in chapter 1, we have seen how we can perform multiplication of two numbers. Let's say we have got 0, 0, 1, 1, which is number 3, and let's say 0, 0, 1, 0, which is 2. When we multiply these out, we can say that this is 0, 0, 0, 0, then 1, 1, 0, 0, and then the rest is 0, 0, 0, and another 0, 0, 0, 0. So in the end, we add them up. So 0, 1, 1, 0, 0, 0, 0. And this is actually giving us 6 in decimal. So this was 3, this was 2, and we have got 6. Now, this was unsigned number. We didn't specify any pluses or minuses in front of it, and it's easy to calculate. But when we consider signed numbers, we cannot use this method. We are not going to get the right result. You might think of converting that to 2's complement version and then multiplying them together. You can try, you are not going to get the right value. So, how are we going to do that? Before we get into the signed part of it, if you consider this simple example over here, for multiplication in typical arithmetic logic unit, we don't have any multipliers. So how do we perform multiplication? We are actually using an AND function which performs some kind of multiplication. Then we perform addition. So inside of our arithmetic logic unit, we have got the logical unit which performs AND or XOR operations, and also we have got an adder which performs addition and subtraction operations. So if we consider that, we can also use arithmetic logic unit without a multiplier, and we can perform the signed multiplication. Now, to do that, we need to use the addition operation, the subtraction operation, and the shift operation. So addition and subtraction operation can be done using an adder subtractor circuitry, and shift operations is just we can use a logical shift, and which we can do that inside of an arithmetic logic unit. Now, let's get into the Booth's algorithm. So to understand the Booth's algorithm, we have got some variables or the parameters that we need to consider. So these are the variables. So if you want to perform m times q operation, which we are going to get the result as a p, m is our multiplicand, as you know, q is our multiplier, and p is our product. We are going to use other two variables, which is a is the accumulator and q minus 1, the bit that comes after q0. Now, as you can see, n bit, n bit, n plus n bit, and n bit. Now, the important thing over here that multiplicand, multiplier, and the accumulator, they have to have the same number of bits for this operation. So for example, multiplicand is 3, multiplier is 2. we have to make multiplier 3 as well, and we have to have the accumulator has got the same amount of bits as well. And when you multiply these things together, you normally get n plus n bit. So 4 bit multiplied together with another 4 bit, you are going to get 4 plus 4, 8 bit product. This is really important, and it's really important in a way that interpreting these bits at the end of the calculation. And n is the number of bits that we are going to use. This also shows the number of times that we need to perform this algorithm. Okay, so the number of bits, and it's actually showing the number of times that we need to perform this calculation. Now, you might ask, what is q minus 1? Q minus 1, when you consider the multiplier, let's say it's 4 bit, so Q3, Q2, Q1, and Q0. On the other side, we also have Q minus 1, which we are going to use. Now, you might ask, what is Q minus 1? I'm going to define that in a minute. Now, when you want to initialize this algorithm, we have to assign some values, because we already know the multiplicand and multiplier, which is given to us in this case, because that's what we are going to calculate, but we don't know the accumulator or Q minus 1. Accumulator and Q minus 1 at the beginning, they are initialized to 0. So Q minus 1 initialized with 0, and then we have got some numbers over here that we are going to use. Now, the aim of this algorithm, or the way that interprets the bits and makes the calculation for signed bits, it actually checks the last 2 bits of the multiplier and the Q minus 1 and perform the operation based on that. Now, let's get into the details of it. There are a couple of things that we need to take care. One of the rule is n number of m, n number of q, and n number of a bits we need to have. So we need to have equal number of bits. This is one of the important things. And of course, as we are doing sign multiplication, we need to consider the sign bit in that bits as well when we want to perform any Boole's algorithm operation. Now, the Boole's algorithm has got its own conditions to perform this algorithm, and these are given in this table. So if you want to perform, if you have got Q0 is 0 and Q minus 1 is 0, or Q0 is 1 and Q minus 1 is 1, we are actually comparing these two. So we have to compare these last 2 bits. If it is 0, 0, or if it is 1, 1, we just need to perform an operation of arithmetic right shift. If it is 0, 1, it's going to be accumulator will have the value accumulator plus the multiplicand, or 1, 0, it's actually accumulator is going to be a minus m. But when we do this operation, or this operation, after that we also need to do arithmetic right shift. So we need to perform arithmetic right shift on both cases. Okay, now as you can see from the table, if it is 0, 0 or 1, 1, we just perform arithmetic right shift. If it is 0, 1, we perform accumulator plus multiplicand stored in accumulator and then perform arithmetic right shift. Or if it is 1, 0, it's going to be accumulator minus m stored in a. So it's m, it's going to be in the 2's complement form. Then we perform the arithmetic right shift. The easiest way of understanding this is to perform an example. So that's what we are going to do in a minute. Now let's see the flowchart of this algorithm. At the start, we initialize the accumulator and the q minus 1 to be 0. We know the multiplicand and multiplier in binary. They have equal number of bits. And then we know that how many steps or how many times we need to run this algorithm based on the number of bits. Then we start comparing q0 and q minus 1. If it is 1, 0, we perform the subtraction. If it is 0, 1, we perform the addition. Otherwise, 0, 0 or 1, 1, we just perform arithmetic right shift. So when you perform subtraction or addition, in the end, we have to perform arithmetic right shift as we already said. Then we decrement the number of steps or the number of times that we need to perform this algorithm, and then we check if n is equals 0 because we have to stop when n is equals 0. Otherwise, we go back and we check again and perform the operation and again until n is equals 0. Then we get the result in the multiplier and in the accumulator. So the binary numbers that we have got in the multiplier and the accumulator will actually show us the result of that operation. So let's give a start and let's do our first example. The first example, it says 3 times 5. Now, for 3 times 5, let's write 3 first. We can write 3 with 2-bit numbers, which is 1, 1. Can we write 5 with 2-bit numbers? No. 5 needs to have 3-bit number. So that means we need to write 3 with 3-bit number as well. So we can just say 0, 1, 1. And on the other hand, 5 is 1, 0, 1. Now we need to add the sign bit. So 3 is going to be 0, 0, 1, 1. And plus 5, it's going to be 0, 1, 0, 1. Then we can also find minus 3. And that is equals the complement of the plus 3. So 1, 0, 1, 1. And minus 5 is equals 1, 1, 0, 1. So we have got the numbers and they are equal number of bits, and then we can derive our algorithm. Now, to perform this operation, we actually need to have some kind of table. So n is the number of bits, which is equivalent to 4. So we have got 4 bits on both sides. So n is 4. Then we need to write the accumulator, and we said that at the beginning the accumulator is 0, 0, 0, 0. And then we have got the multiplier. So which one is multiplier in this case? M is 3 and Q is 5. So Q is our multiplier and we need plus 5 over there, which is going to be 0, 1, 0, 1. And then we also have Q minus 1, which we already set, and that is initialized to 0. And the last thing that we have is the operation that we are going to perform. Now, we have got the initialization, we have got all the numbers that is required, and now we are ready to perform the algorithm or the Booth multiplication. So in order to do that, we need to compare that bit and that bit. 1, 0. Let's go back to the table. 1, 0 is A minus M stored in A. So let's write that down. A is A minus M. Now, what is our A? A is 0, 0, 0, 0, and M is, in this case, it's going to be a minus M, so M is 3 minus m is minus 3. So 1101. 1101. Then we perform the addition. So this is going to be 1011. Now we have got 1101, and this has to be stored in the accumulator. So inside of the accumulator we will have 1101. We write Q as it is, 0101, and we write Q minus 1 as it is. So it's 0. Now, the next thing that we need to do is the arithmetic right shift. So to perform arithmetic right shift, I don't know if you know arithmetic right shift, but this is how it is. So the first most significant bit stays as it is. Then the most significant bit also shifted to the 1, and then that will be shifted to the 1, and that will be shifted. So that's 1110. Then that 1 will be shifted over here, that 0 will be shifted over here, 1 0, and then 1. So we have got a new number which is already shifted, and now our n is going to be 3. So we are decrementing it. Then we check again. The last two bits, it's 0 1. 0 1 means a plus m. So the next operation is a plus m. Our a is 1110, and then our m is, which is 30011. So when we add them up, this is 1 0 1 0 1 0 1. We discard the end carry and we write the accumulator as 0 0 0 1, and then we write the multiplier 1 0 1 0 as it is, and that will be 1. Now we do another arithmetic right shift. So that arithmetic right shift, we have got 0, and that 0 is also shifted over here. 0 0 1 1 0 1 0. So we actually perform arithmetic right shift over there, and now we reduce that to 2. Then we check again until we have got 0 on n. Now it is 1 0. That means we have to perform a minus m operation. Our a is 0 0 0 0, and our m is minus m is 1101. So we are actually performing this operation again. I'm not going to write it over here, I'm just going to write the result of it. So our accumulator now is going to be 1 1 0 1, and our Q is 1101, as we already have got that. And our Q minus 1 is 0. So now we have got a new value that we need to shift. So to perform that shift, we need to have arithmetic right shift. That means we need to keep the first bit as it is, then shift it to the right as well. That will be shifted. That will be 0 1 1 1 0 1. And now we have got the new value, and our n is 1. And we compare it again. So 0 and 1. Now 0, 1, it's going to be a plus m. That means a is a plus m. And our a is 1110 and our m is 0011. This is actually repeating that operation. So we can just write accumulator as 0001 and our multiplier is 1110 and our q minus 1 is 1. Then we have to perform arithmetic right shift once again, and that's going to be so 0 0 0 0, then 1 1 1 1 0. Now that's n is equals 0. That means we have to stop there. This value or this number is going to give us the result of our multiplication. So as it says over here, the result in Q and A. So that means the accumulator and the multiplier output will actually give us the result of it. So this is what? We have got 0, 1, 2, 3 ones. That means this part is representing 15 and that's 0. So we can just say this is plus 15, which is what we were expecting when we perform 3 times 5. So this is how we can run the Booth's algorithm. But on this one, we didn't specify any negative numbers, and we are going to do another example which shows the relationship with the negative numbers as well. So the rest of these slides actually shows how these operations that I have performed on the whiteboard are going to be happening. So you can follow these step by step and you can see how it is performed. And in the end, as you can see, it's got 0, 0, 0, 1, 1, 1, 1 in the multiplier part, which is equivalent to 15. So that's pretty straightforward. Try to solve by yourself. Try to perform operation with the different numbers. Again, if you have any question, please do not hesitate to ask me. Now, the next example is minus 6 times 7. Now, if you perform minus 6 times 7 with an ordinary multiplication, binary multiplication that we have done in the first chapter, you are not going to get minus 42. So, I don't suggest you to do that, but if you want, you can try it to see that you're not going to get the right number. Now, let's consider 6 first. 6 is equals 110, which is a 3-bit number. 7 is equals 111, which is another 3-bit number. So we can represent these with 3 bits. So that's 6 and the 7 is 111. Now, plus 6. Plus 6, it's going to be having another bit in front of it which represents plus, which is 0, 1, 1, 0. And plus 7, it's going to be 0, 1, 1, 1. Now we have got signed, positive signed numbers. Then let's find out the negative ones. So minus 6, it's going to be the 2's complement of the plus 6, so 0, 1, 0, 1. And minus 7 is 1, 0, 0, 1. So as you can see, we have got the 2's complement of both numbers. So this represents M and that represents Q. Now we are ready to derive our table again. So N, it's going to be 4. A, it's going to be 0, 0, 0, 0. And then Q, it's going to be plus 7, so it's going to be 0, 1, 1, 1, and then we have got q minus 1, which is 0 when we initialize it, and then we have got the operation that we need to have. Now we are ready to start for the algorithm. We check q0 and q minus 1, which is 1, 0. Let's go back to the table again. 1, 0 is a minus m. So a is a minus m. That means our a is 0 and minus m. So minus m is actually 6. M is 6. Minus m is minus 6, isn't it? Think about it. Or is it the other way around? Now, the important thing over here, our m has to be, if we go back to the example, what is asking to us, our m has to be minus 6. Okay, so m is not 6. M is minus 6. And 7 is our q, because this is m times q, which is equals to p. So that means our m is minus 6. So minus m minus 6 will actually give us plus 6. I'm going to repeat once again. M over here is minus 6. So that means minus m is going to be minus 6 minus m, it's going to be plus 6. Minus minus is going to be plus. And 7 is just our q. So we can say that m is minus 6 and q is 7. Now, that means we have to perform the operation as follows. So 0, 0, 0, 0 plus 6, which is 0, 1, 1, 0. So when we add these two numbers, we are going to get 0, 1, 1, 0. Now this is our naive accumulator. So that will be written over here. So 0, 1, 1, 0, our naive accumulator, and then 0, 1, 1, 1 is our still the multiplier bit, and we have got 0. Now we have to do arithmetic right shift. So arithmetic right shift, we'll have 0, the first bit, and then 0 is shifted, and then 1 is shifted, and then 1 is shifted, 0 is shifted, 0 is shifted, then 1, and that one will be shifted over here. Now we have got the new value, and our n is 3. We decrement it. Then we repeat again. So 1, 1. Now we have got 1, 1. If we go back to the table, 1, 1 is actually just arithmetic right shift. So we need to perform arithmetic right shift without any arithmetic operations. Arithmetic right shift, this is going to give us, so 0, 0, 0, 1, 1, 0, 0, 1, and then 1 over here. Now that is n is equals 2, because we just perform arithmetic right shift, and that's it. Again, we have to check the last bits. Now the last bits is 1 1 again, so that means it's another arithmetic right shift. So that means it's going to be 0 0 0 0 and then 1 1 0 0 and 1. Now that's our naive value after arithmetic right shift. Again, we need to compare for the next bit, but this is equivalent to 1. Now, the next one that we need to consider, we have to do another comparison. So that is 0 and 1. 0 and 1, it's a plus m. So we can say that a is a plus m operation. What is a? A is 0 0 0 0 and m is 1 0 1 0. So when we perform the operation, we are going to get 0 1 0 1. Now this is our new value 1 0 1 0, and this is 1 1 0 0, and that is 1. Now we need to do arithmetic right shift. So in that arithmetic right shift, we are going to get 1 1 0 1 0 1 1 0 and then 0. So we have got a new value, but the number of steps is 0 now. So that means we came to the end of our calculation. All we just need to do is to find out what will be the value over there. So I'm just going to repeat once again. As this is 1 0, we have to perform a minus m. So we performed a minus m, we got 0 1 1 0. So 0 1 1 0 is there. Then we perform arithmetic right shift. So that's shifted and we decremented n. Now we have got 0 0 1 1 0 0 1 1. Now 1 and 1 on both, that means it's going to be only arithmetic right shift. So we perform arithmetic right shift, and that will be 0 0 0 1 1 0 0 1, and 1 is shifted. Again, it's 1 and 1, and this is decremented to 2. That means it's another arithmetic right shift. So we shift it once again. This is going to be all zeros, and that's going to be 1 1 0 0, and that one is shifted to 1. Now it's 0 1. We perform the addition, a plus m, which we are going to get 1 0 1 0. So that 1 0 1 0 is written for the new accumulator value, and we have got the q as it is and q minus 1 as it is. Then we perform another arithmetic right shift, and this is going to be 1 1 0 1 0 1 1 0. Now, is this the right number? Let's check. So that 8 bits actually is going to represent the number that we need to have. So 1 1 0 1 0 1 1 0. Now, as we are expecting minus 6 times 7 to be minus 42. That means this value can be in the 2's complement form. So let's check. That is going to be 0. We are taking the 2's complement. So 1 0 1 0 1 0 0. Now, is this 42? So 0 1 2 3 4 5. This is 32 plus 8 plus 2, which is equivalent to 42. So this means that is equivalent to minus 42, and we perform the operation correctly. So you can check your result by using this, taking the 2's complement of it and finding minus 42 over there. So I hope this is clear. We have done minus 6 times 7, which is minus 42, using the Booth's algorithm, and you can also find the similar calculations on the slides. This is done with the 5-bit. I've used another extra bit over there, but as I said, as 6 is 3 bits, you can just use 110 and add another sign bit, but this is done with the 4-bit. It's up to you. In the end, the most important part is A, Q, and M has to have equal number of bits. So now let's do another example, which we have got minus 10 times minus 18, which is equals 180. Now this is another good example because we have got more than 4 bits in this case. It's 2 negative numbers, and in the end the result is going to be positive. It says m times q, it's going to be p. Now in this case m is minus 10 and q is minus 18, and we will have p as 180. Now let's find out 10 and 18 in binary number first. Now 10 is 4-bit, 1010, but 18 it's going to be 5 bits. We cannot represent 18 with 4 bits. So that means for 10 we can say that 1010 is 10, but we need to have 01010. So we need to have it 5 bits. And 18 is what? It's 16 plus 2. 16 is 2 to the power 4. 2 to the power 3 is going to be 0. 2 to the power 2, 4 is going to be 0. 2 to the power 1, 2 will be 1 and 0. So 16 plus 2, it will be equivalent to 18. Now we have got two 5-bit numbers, and we need to take care of this using the sign bits. So we need to have plus 10, which is equivalent to 0, 0, 1, 0, 1, 0, and plus 18, which is equivalent to 0, 1, 0, 0, 1, 0. So now we have got 6-bit two numbers, and we can take the 2's complement of that. So minus 10 is equivalent to 0, 1, 1, 0, 1, 1, and minus 18, it's equivalent to 0, 1, 1, 1, 0, 1. Now we have got 2's complement version of these numbers as well. Next thing to do is to start to our algorithm. Now m is minus 10 and q is minus 18. That's what we are going to use. Let's write it down. So n, how many bits do we have? We have got in total 6 bits. A needs to be 6 zeros initialization. So that's A. And then Q it's minus 18, which is 1, 0, 1, 1, 1, 0. And our Q minus 1, it's going to be initialized as 0. And then we have got the operation, which we are going to perform. Now, we are ready, we initialized it, and we can start comparing the bits. Now let's start with 0, 0. I'm going to open up our table again. to see the operations. You need to remember the table or you can check it out. So 0, 0, it's actually arithmetic right shift only. So we can say that we'll perform arithmetic right shift. That means this is going to be shifted 0, 0, 0, 0, 0, 0. That 0 will be shifted over here because that's representing both. That's that one, that's that one, that's that one, and that's that one. So 1, 0, 1, 1, 1, and that 0 will be shifted to the right. Now we have got a new number. Then we need to check that number. So 1 and 0, the last two bits. So 1, 0 is a minus m. That means a minus m. So we need to do what? Our a is 0, 0, 0, 0, but we need to subtract from m. Our m is minus 10, minus 10, it's going to be plus. So that means we have to add 0, 0, 0, 0 plus 0, 0, 0, 0, 0, 1, 0, 1, 0. So we can write it over here. 0, 0, 0, 0, 0. So that's 4, 5, 6 bits. And then we have to add 0, 0, 1, 0, 1, 0. And this will be 0, 0, 1, 0, 1, 0. So now we have got the new accumulator value, which is 1, which is 0, 0, 1, 0, 1, 0. And then we have got Q 0, 1, 0, 1, 1, 1, and Q minus 1, which is 0. Now, as we have done arithmetic right shift at the beginning, our n is going to be 5 over here. Then we do another arithmetic right shift after we have got the arithmetic operation. So this is going to be 0, 0, so 4 these, and then 0, and then 1, another 0, another 1, that's 0, that's 0, this is 1, 0, 1, 1, and then 1 shifted. Now we have got the new value and our n is going to be decremented to 4. So we have got 1, 1. 1, 1 is just arithmetic right shift. Arithmetic right shift that we are going to perform, and that will be 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, and then 1 on the last one. So this is going to be 3 now, as we have done arithmetic right shift. And we check again these two bits. This is 1, 1. 1, 1 means it's another arithmetic right shift. So 0, 0, 0, 0, 0, 1, then 0, 1, 0, 0, 1, 0, and then that will be 1. And our number of cycles, it's going to be decremented to 2. Now we have got 2. We have to check the last two bits, which is 0, 1. 0, 1 means addition. So we need to perform a plus m. Now our A is 00001 and our M is 110110. So let's write it down. 00001 and we have got 1 0, sorry, 1 1 0 1 1 0, and we have to add those. So that is going to give us 1 1 1 0 1 1. Now we have got a new accumulator value, which is 1 1 0 1 1 1, and then Q is 0 1 0 0 1 0, and then we have got 1. And the next thing to do is to arithmetic right shift. And let's do an arithmetic right shift. 1 1, then 1, then 0 1 1, that one shifted, 0 1 0 0 1, and that 0 is shifted. So now we have got the new values, and our n is going to be 1. And we have to compare, which is 1 0. So now 1 0, it's going to be a minus m. Now a minus m, we have to perform, and our a is 1 1 1 0 1 1, and our m is, it's minus m, so it's going to be plus 10 0 0 1 0 1 0. So that is going to be 1 0 carry 1 1 0 carry 1 0 carry 1 0, and we have got carry 1. We discard it. So once we discard it, we have got a new accumulator value, which is 0 0 0 1 0 1, and then Q is 1 0 1 0 0 1 and 0. Now arithmetic right shift again, and this is going to be 0 0 for both, and then another 0, then another 0, then 1, and then 0. That one is shifted, 1 0 1 0 0, and that one will be over here. Now the number of steps is 0. That means we can stop, and let's check the value that we have got. So we need to get A and Q together, and what we have got over here is 0 0 0 0 1 0, then 1 1 0 1 0 0. Is this the right number? Let's check it. So we have got 0 1 2 3 4 5 6 7 8 9 10 11. Now we have got 7, which is 2 to the power 7, which is 128. Then we have got 32, 116, and then we have got 2 to the power 2, 4. So we have got 128 plus 32, that means 160 plus 20, that means 180 as a product number. So we have got the right values over there. That means we performed the both algorithm correctly. You can try any numbers, you can play around and check it out if you're going to get the right values. So in your lab, pre-work and for the final lab, you have to use this approach to perform the operation required for the finite state machine. I hope this is clear. If you have any questions, please do not hesitate to contact me or ask me in the QA session. Thank you very much.